Hey everybody, it's Bob Crossan, Senior Managing Editor for Water and Waste Digest, and today I'm here with Andrew Gilmore. He is Vice President and MBR Chief Technologist for Carollo, and I also am here with Amos Branch. He is Water Reuse Technologist for Carollo. So today we're going to talk a little bit about membrane bioreactors, also known as MBR. I wanted to start from a high level. Can we get some definitions? Can you explain a little bit what is MBR, just right off the top?
Yeah, absolutely. Thank you. I'm glad to be here too. So MBR is, like you said, membrane bioreactor, and it's another activated sludge process that's evolved over the past 2 decades. Historically, we've treated wastewater using more conventional processes, MLE process, whatever it may be. And then back in the research days, people started looking at how can they take these polymeric membranes and bring them into wastewater as a separation device. And some of the early membranes back in, say, the late 90s and early 2000s, when we really started to utilize that technology to bring the membranes in and, in essence, take filtration, bring the filtration into the secondary process, which then eliminates clarifiers, eliminates that tertiary filter, and brings it all to one. And then in doing that, you really concentrate, or the word we're using these days in the wastewater field is intensify the process by doing more and less space. So it's a process, again, that we use to reduce the different things we're worried about for water bodies, whether it's nutrients or pathogens, whatever it may be.
Mm-hmm. Yeah. So what types of facilities tend to find success with MBR over others?
Yeah, so there's interesting questions. So I think the facilities that find success with it are a couple of different categories. Some are the ones that are more remote, so smaller. So there are situations where you want a small satellite treatment plant that's closer to, say, water reuse. And MBR couples well with that because of the small footprint nature and the high quality of the water. So if you want to build something right adjacent to a golf course, say, for example, or you have a very large collection system with a big main plant, but trying to create higher level water at that main plant and then pump the water tens of, or 100 miles up into an area, uphill even, to where the water is needed, can be cost prohibitive, as opposed to building one of these small plants into a community that can be really blended in too aesthetically. And I didn't realize, as well as it can become a community asset, and you can have, like they've done in areas such as Brightwater in Washington or in Victor Valley, California. They've done a good job of trying to explain to the residents that this is something that augments the community because they bring reuse right nearby. The other place we're starting to see a lot of success with MBR technologies is expansion of existing plants that are landlocked. So a lot of these plants, if you think about the history of wastewater treatment, these plants were called at one time, water pollution control facilities, because we're trying to control the pollutants that went to, Waters United States, whatever it may be, or groundwater. And then they became water reuse facilities or water reclamation facilities. We're trying to reclaim this water to use it to offset potable needs. And now we're starting to get to something what Amos will talk about probably here soon, is getting into potable reuse, and now using membrane as part of the barrier in that treatment process. And that takes us back to the retrofit of existing plants. There are a lot of plants now that are built as water pollution control facilities, and they were built out at the outskirts of society at the time. But of course, as urban sprawl has happened, now these facilities are landlocked. And because of what they used to control, the pollutants they used to control are different than the ones we're controlling now. So if in the past they were just oxidizing, and now they need to remove nutrients, you have to do more in the same space, and that reduces the capacity, right? Because you have to do more in that biological process. MBR comes in well because now you can intensify, the intensification concept again. You can intensify and do more in that same footprint and reach your goal within that footprint you do have. So that's where MBR really is working well, that what we're seeing out there. And then, Amos, maybe you can talk about what we're seeing, success, the early success we're seeing in some of the work that you've been doing on potable reuse.
So At the moment, there's, certainly in California, there's a pretty well-established full advanced treatment scheme to do water recycling. So that happens at Orange County Water District. You have a conventional wastewater treatment plant upstream. It has activated sludge. It has big clarifiers that, as Andrew said, take up a lot of area. And then you move to membrane filtration, reverse osmosis, and then UV advanced oxidation. Now, in trying to meet the capacity of future plans with population growing, some of these plants, they need to start combining, and they do get pretty significant space savings, sometimes up to 4 times, or with the same area, they can treat to a much higher or much more efficient nutrient removal level. Because what you've done is you've essentially removed that clarifier area and you've replaced it with a membrane system, which is a lot smaller. Now, some of the research we've been doing has actually pretty well suggested that we can put these membrane bioreactors in, and they can, from a pathogen removal standpoint, they can functionally replace having that whole conventional activated sludge treatment clarifier system and the microfiltration system, and still meet public health goals for pathogen removal quite easily, as well as providing all these other benefits around enhanced nutrient removal and upgrading the capacity of existing installations.
Yeah. Well, when you're implementing these, or you're getting these installed, or you're transitioning to that, what are some of the critical pieces you need to get right to make sure that it functions the way it should?
Yeah, so that's one of the things is the industry has evolved over the past 2 decades, and it's been a great thing to watch too as it's gotten better. So one of the early things that folks learned is screening is really important. So depending on the type of membrane, whether it's a hollow fiber or flat plate, is very important to protect that membrane from small materials, whether it's hair or bigger particles. So early membranes, some of the ones that were built in the late 90s, didn't know because they didn't know we didn't know, right? And so we had larger openings than we should have, and we had some issues with the membranes. And then so over time, it got tighter and tighter. And now, the standard is a 2 millimeter or maybe 3 millimeter, depending on the type of membrane, perforated plate has become the standard because we need to protect those membranes. And that has worked into the warranties of the membranes. That's one of the things that people are not getting right, as well as choosing a really good screen. There's been some issues with underperforming screens, or screens that have had issues with bypasses or failure points. The things get by and then impact the screens, as well as the wash compactor, right? You take the screens out, you got to compact and wash the material. But if the holes in that wash compactor are bigger than the screen size itself, and it gets recirculated after the screen, well, then you take it out and then you put it back in. So we've seen that problem in some places, and that's getting better. Move into the next step, which is then the biological part, the bioreactor, or the aeration basin, as a lot of people call it. That design is really important because it has to couple with the membrane design. And some of the early designs really looked at it as the membrane is a black box. You can see some of the early designs were a bunch more by vendor, not so sure, let them take all the responsibility. And that was okay at the time because there was a little bit of uncertainty of how these things were going to operate, and making sure there's a responsibility from the supplier. But we've evolved that understanding to know that we need to look at that as a complete system, and need to be a completely designed system in collaboration with that membrane supplier. And that's improved the reliability and robustness of these systems. And then on the bioreactor side, into the membrane side, one of the things that we've seen some of the early membranes is a really good way to pull foam or scum or filamentous material that builds up on the top. The membrane itself is a barrier. It could be 0.2 or 0.04 microns, so nothing can get through, right? So any materials like this filamentous material or foaming gets trapped. In a conventional plant, you got clarifiers or a skimming mechanism, just pulls it off, you're all good. Here it gets trapped, and there's places where they haven't been able to pull it off, or they're just trying to pull the foam off by itself. It's not compressible, not pumpable, and it's choked some of these plants. So that's something that's evolved over time. The other thing is the energy efficiency and the chemical usage. Some of the earlier membrane designs were using a ton of air to scour to try to keep them clean, using a lot of chemical to clean them as well. And that's something, especially over the last 10 years, the membrane suppliers have done a fantastic job of trying to reduce the amount of chemicals and energy usage, because we all know that life cycle is what drives a lot of decisions. So if the life cycle on a system like MBR is out of sync with other technologies, it won't be selected unless they have to, right? Unless an owner has to because of footprint or some other reason. And that's something that especially the last 10 years, has really gotten dialed in. So I think that's some of the different things I've seen that are important, have evolved, and has gotten a lot better in the design world and operation side. The other thing too, just quickly on this, is I always think of the concept of, what to expect when you're expecting, right? So for an owner, making sure there's really good education on what they're going to get relative to the MBR, and getting good training, because it is different if they're working and operating an existing activated sludge plant. It will be a shift in mentality of how you run an MBR plant, as far as the level of automation, the level of PLCs, the level of actuators and instruments they need to maintain to make this system run, as opposed to an activated sludge plant, which is a little different philosophy.
Yeah. So one of the other things, you can do some advanced stuff with MBRs, and I know, Amos, you kind of fall into this wheelhouse. Could you talk a little bit about some of those advanced things that you can do?
So this particularly applies to water reuse, and obviously then you're taking sewage, you're treating it to a very high level, and then someone's potentially going to drink it if it's potable water reuse. As a move now, indirect potable reuse has been around for a really long time. It's been practiced, it's been proven safe. In California, at least, there's a reasonable definition of what constitutes indirect potable reuse, and that's having about 2 months minimum worth of some sort of environmental buffer. So whether that's a groundwater system or whether that's a surface water reservoir. And in addition to the treatment or potential treatment in pathogen decay that happens in those reservoirs, what it really gives you is response time. It means you have a month out of that 2 months to realise there's an issue and to correct that with your system. When we start moving to direct potable reuse, that means connecting that advanced water treatment plant into the distribution system or just up the front of a water treatment plant. You lose quite a significant portion of that response time. And what that really means is you have to focus on advanced monitoring techniques and really good process control in order to actually assure that you're getting that pathogen log removal. Measuring pathogens isn't easy. You're talking about, if you're looking at things like Cryptosporidium and Giardia, probably about a day of lab activities. It then gets sent, a day of site activities. It then gets sent to a lab, and sometimes turnaround times can be a month. So in that time, you already don't have your answer. What you need to move towards, and what is becoming more accepted as a technique to control these systems, is a hazard and critical control point philosophy. So that means you define at each treatment stage, including the MBR, what the barrier is, what does the most work controlling pathogens, and then you go and prove out what online monitoring techniques that give you real-time information can tell you about the pathogen removal performance. So one of the interesting Water Research Foundation projects we're working on at the moment is actually exploring and is going to ground truth those particular monitoring technology options for membrane bioreactors. So they include more simple and proven things like turbidity. We're going to try and develop correlations there with pathogen removal, including pressure decay testing as well, which is another commonly used membrane integrity test, which isn't quite suitable for all membrane configurations. And there's also more advanced microorganism surrogates. So pepper mild mottle virus is one. It's a plant pathogen. It's everywhere because everyone likes a bit of chili sauce on their food. It means it ends up in the sewage. And there are companies now developing very rapid measurement techniques for analysing that pathogen, and it could be one of the answers to getting a surrogate to prove out the pathogen removal performance of these systems in a really short time scale.
Well, thanks so much. We do appreciate your time, and we'll see you next time.
Thank you.
Thank you very much.